Okay, let's talk about K-select. This is a really fun and cool algorithm, in my opinion. It's one of my favorites. A little bit complicated. Okay, so K-select. K-select means select the kth smallest element of a list. So if I have a list like this, and I'm trying to find K-select on this list of 3, that means tell me if I sorted this list, what would be at index 3? In other words, what is the 4th smallest element, since we're using zero-based indices, of this list? And that's 4. So if we run this program, we indeed get 4, which is what we want. Also, if I have this list of numbers 0, 1, 2, 3, all the way to 8,999, what is at index 222? 222. If I shuffle the list, K-select still returns 222. And here's the cool part. You might be thinking, okay, well, we can implement K-select by just running sorting algorithm on the list and then selecting at index k the element. But that would take O of n log n time, because sorting takes O of n log n time. The brilliance of K-select is that it runs in O of n time. It runs in linear time. And to show that, I have plotted here the time complexity, and you can see that it's indeed a line. So how do we shave off that log n? Well, that requires a little bit of ingenuity, and that's what K-select provides. So let's talk about how K-select works. K-select will take a list, it will find a pivot. Well, let's talk about the base case first. The base case is if the list is empty, or we're trying to find the kth smallest element and k is greater than the length of the list, then obviously that doesn't exist, so we're going to return none. If the list is sufficiently small, if it's less than 10 elements, we're just going to sort the list and find the kth smallest element, because that's O of 1 work, because 10 is a constant. All right, for the recursive step, we are going to find a pivot. And we are going to take all of the elements in the list and we're going to partition them by the pivot. So every element in the list that's less than the pivot is going to go into a list called left. And everything in the list that's greater than the pivot is going to go into a list called right. Now, if we're selecting the kth, now pivot currently, the index of the pivot value is the same index that the pivot value would be in if the list were sorted, right? Because if the values were like 0, 1, 2, and the pivot has a value of 5, and then in the right we have whatever jumbo, doesn't have to be in the right order. Everything to the left is going to be less than the pivot. Everything to the right is going to be greater than the pivot. So the pivot's in the right place if the list were sorted. So if we're selecting, in this case, k is 3, well, the pivot is at index 3. So the 4th smallest element in the list is going to be the pivot. So that's what this line says. It says if you're trying to find the kth smallest element and the pivot's in the kth smallest element place for a sorted list, then just return the pivot. The key is if the k is smaller than the pivot index, then that's equivalent to just running K-select on the smaller case, right? So if we're trying to find the 3rd smallest element and the pivot is at index 5, then that's the same as just finding the 3rd smallest element on the left. So that's what this does. Alternatively, if we're trying to find the 10th smallest element and the pivot's 5, that's the same as finding the 10 minus left minus 1 element on the right, right? Because if we have 3 elements on the left and we have 1 element for the pivot, then whatever is the 10th smallest element of this entire list is just going to be the 10 minus 4th smallest element of the right. Okay, so this is the recursion. Now let's talk for a second about how we're able to find the pivot. So we want a pivot that's going to be splitting the list fairly evenly. So ideally, the pivot would make it so the left has 50% of the elements and the right has 50% of the elements. That's if the pivot were the median, right? Because if we had a pivot that just put like one element in the left and like 1,000 elements in the right, then that's pretty useless, right? So how do we ensure our pivot is going to be splitting the list evenly? Well, there's a way to do that. There's a clever way to do that without too much computation. And it's called finding the median of medians, this is just so cool. So if we have our list, and the list consists of L1, L2, L3, L4, L5, Ln. What if we wrote it a certain way? What if we wrote it as groups of 5? Okay? So we're going to have the first group like this, L1, L2, L3, L4, L5. Then we're going to have L6, L7, L8, L9, L10, L11, ... And this is going to go all the way to Ln. What if I took an individual group of 5 and sorted it such that it's in ascending order? Okay, so now maybe we're going to have it be like L2, L1, L4, L5, L3, whatever. It's sorted so that the smallest element's here, the largest element is here. So the middle element, the third element, is going to be the median of this small list. And what if we do that for all the groups, okay? Then this is the median of this group. This would be the median of the second 5 group. This would be the median of the third 5 group, and so on. So this whole column is just all the medians. And that's what the code's doing here. It's taking the list and it's going to split it into groups of 5. And the 5s are then going to be sorted. And then they're going to be extracting the middle element, which is the median. And then all the medians are going to be added to this list medians. So this over here is the list of medians. But we want to find the median of medians. So we are going to take the medians, sort them, and then find the middle element. Now, I'll get to this in a second because technically I'm not supposed to do that, but I did it because I couldn't figure out the other way to do it. But that doesn't matter for accuracy. We are finding the median of medians. So the median of medians is going to be this guy, right? If we have 3 other medians here. Why is this a good partition? Why is this red guy a good partition? Because the way we defined it, we sorted it, okay? We sorted it so that the medians are in ascending order here. So this median is bigger than this median's bigger than this median's bigger than this median. That's just how we wrote it out because we sorted the medians. So the reason why this is a good partition, a good pivot, is that this is greater than that, which is greater than that, which is greater than that. This is also greater than that, which is greater than that. If we remember that this is a group of 5. Okay, so if this is E3 and this is E2 and this is E1, this guy is greater than that and that. So this E3 is greater than all of the elements here. I'm just going to circle this. All of the elements in the purple box are less than E3. How many elements is that? Well, this box has 3 on this side, and it has n divided by 2 on this side. If we include this, right? How big is this whole box? This is n over 5, actually. And this is 5. So actually, this should be n over 2 over 5. So what's the ratio of the purple to the whole thing? It's 3 times n over 2 divided by 5 over 5 times n divided by 5. N's cancel, and we are left with 3 divided by 10. 30%. This pivot that we selected, the median of medians, is greater than 30% of the elements. Good. We have a 30-70 split with our pivot. Okay, so let's talk about the runtime, because that's really the only thing that's important about K-select, is to get rid of that log n in our runtime, to make it linear runtime. If we have K-select, we can say that T of n is how much time it takes K-select to run on a list of size n. This first step is the base case. Okay, so T of n is going to be O of 1 time for n less than 10. Okay, we have to find the pivot. What's the runtime of finding the pivot on a size n list? Well, when we're finding the median of medians, we have our list of medians. To find the median, technically, I'm supposed to use K-select. Okay, I'm supposed to take the medians and tell me the middle element using K-select. Now, I didn't do this because I was running into some problems with recursion, so I sorted the list. But if we were to do that, then the runtime would be T of n over 5 for find pivot, because the length of the list of medians is 1/5 the length of the list of the original list, because there were 5 elements in each group and there's 1 median per each of the 5 group. Okay, so this is for find pivot. For partitioning, that's O of n work. I'm going to call it some constant. Let's just say O of n. We're just going to say it's C1 of n. Okay. Recursion. And actually, if we're going to do that, we should make this a less than or equal to sign. We are only calling K-select on the left or the right. We're not doing both. Worst case scenario, if we have a 3/10, 7/10 split, the worst case scenario is that we're calling it on the 7/10 side. So let's do that. All right, so we have ourselves a recurrence relation. How are we going to solve this? How are we going to show that it's linear? Let's say we're going to use induction. Let's say that our inductive hypothesis is that T of n is less than or equal to, what constant should we use? D of n. We know that this is true for the base case because if it's O of 1, then that's going to be true. So for our inductive step, we can assume the inductive hypothesis is true for all n between n and k. We want to show that the inductive hypothesis holds for n equals to k, which would mean that t of k is less than, let's just plug in n equals k. There should be an n here. Okay, so now we can do some expansion here because of our inductive hypothesis assumption. We know that this must be less than t of k we know that this must be less than d of k over 5, and this must be less than d 7/10 k. Okay, so that means that t of k is less than or equal to 1/5 dk plus c1k plus 7/10 dk let's just make d greater than c1 so that we can then write this equation as this, right? Because if we say that c1 is less than d, then c1k is less than dk. And we can do that because c1 is fixed. Okay, and then this is going to be 1/5, so that's 2/10 dk. Yeah, I'm actually going to say it's 1/10 dk because we can say that c1 is less than 1/10 d because we can make d whatever we want. This is going to make the math better, easier. So this is going to be plus 1/10 dk plus 7/10 dk. Hey, guess what? That's 10/10 dk. That's less than dk. Boom. Inductive step complete. All right, so we've just shown through induction that t of n is less than or equal to dn, which is equivalent to saying that it's O of n. It's linear. And that's what we saw in our chart. We saw that it was linear. Here's a line. So that's very cool. That means you don't need to sort a list. If you just give me a list of 1,000,000 numbers and you ask me what's the 300,000th smallest number, I don't actually need to sort the list to tell you that. I can run k-select on it and tell you in linear time. So there you go, there's k-select. Very cool algorithm. Oh, and the last thing I should say is that the C++ version also works. It's the same logic except, yeah, C++. I used some pairs to keep track of the index and value. I did that in the Python as well. The keying was kind of a mess. So once again, I am supposed to run k-select for our analysis to work on the medians instead of sorting, so we can avoid that log n, but I couldn't get it in the C++. It was just giving me some nasty errors. But at any rate, this should work just fine. The chart still showed that it was near linear, so it doesn't seem to have made much of a difference. So yeah, cool. Okay, that's it.